let's go ahead and do part K now. Okay, so everybody look at item K on this worksheet. So we're still talking rectilinear motion. We're still in question number 1. It's still x of t. We got this 4th degree polynomial as the position function on the interval from 0 to 7. And part K, and I'm going to actually write the question here so we can talk about it. Part K says, when is the object speeding up? Oops, there's no P on that. Speeding you. Okay, when is the object slowing down? When is the object slowing down? And we understand that an object can be, we've already went through this, right? An object can be a person, an object can be a particle of light, an object can be, a car, a bicycle, right? Lots of objects. Okay. When is the object speeding up? When is the object slowing down? Okay, here we go. In order to understand this, in about 3 or 4 minutes, I am going to give you a concrete way of answering this question that will require no understanding.
Good.
Understand? Okay. All right. I'm going to give you a concrete way of answering this question that requires no understanding. That's not what I want for you, but I still want you to be able to answer the questions on the test. Some of you will benefit from the understanding, which is why I'm going to go through the concept first. Okay? All right. Also, we are strictly doing this analytically. I am not going to put any graphs on this test, or on this whatever, okay? You will need a graphing calc. You can make a graph of it. What I mean is remember how I would ask questions analytically, then I would say, hey, just looking at this graph, answer this question. I'm not doing that this time. Probably, after we get into integration, we will revisit motion, and I will teach you how to answer all these questions with just graphs as well. Okay? But for now, I just want you to be able to do this analytically. Okay? All right, here's the deal. When an object is moving, okay, if it is, well, there's 3 possibilities. It is either at rest, or it is speeding up, or it is slowing down. That's it, right? If it's stopped, it's at rest, right? We already know that happens when...
Change direction.
Right, but what is our technical analytical term? When which function? When velocity... But let's say it analytically. That's a graphical phrase. When velocity equals 0. When velocity equals 0, right? So when velocity equals 0, that means 0 speed, no direction, right? And something with no direction and 0 speed is not moving. It is at rest. So if the object is not at rest, it is either speeding up, which means that its velocity is moving away from 0, or it is slowing down, which means that its velocity is getting closer to 0, approaching 0. An object can't stop without first slowing down. An object cannot stop without first slowing down. If an object speeds up, it can't stop unless it slows down.
Well, what happens when you hit a brick wall?
You slow down really fast.
Okay.
Does that make sense?
Wait, what about like a heart attack?
It's still if you go down to the billionth of a second, you will see things. Do you understand what I'm saying? A heart attack, when you see, nowadays it's easier to understand because our phones have slow-mo. Right? If you slow-mo a heart attack or slow-mo, a car crash, you can actually see the object slowing down. Well, not a car crash, really. So here's the thing, is this is what a lot of people say, is they'll say, okay, let's say you're in a car and you are hitting the gas. So the speedometer is doing this. It's going up. You're speeding up, and then while that's happening, you hit a brick wall. My argument is that when the first molecule of the front of the vehicle made contact with the thing that it was hitting, it started slowing down. It experienced resistance. It experienced backwards force. Does that make sense? Okay? Therefore, even though it would be an extremely steep change in velocity, it is nonetheless a curve.
Because you
Yeah,
still
slowing
losing
down.
energy when you hit the wall.
See this? Yeah. And eventually, it is at rest after it's done with its, mess. Okay? So, are we doing okay? All right, so there's three possibilities. An object in motion is either has a velocity of 0, or it has a velocity that is moving away from 0, or it has a velocity that is moving towards 0. Okay? Can we just for a little while ignore the 0, the at rest, and then just say that an object is either speeding up or slowing down? Is that okay? For now? Okay? All right. I'm now going to expand that. Instead of an object doing 2 things, I'm going to say the object is doing 4 things. Okay? The object is either speeding up in a positive direction, or it is slowing down in a positive direction. Or the object is speeding up in a negative direction, or the object is slowing down in a negative direction. In fact, typically what will happen is an object will speed up in a positive direction, then it will slow down in the positive direction, then it will stop. Then it will speed up in a negative direction, and then it will slow down in the negative direction, and then it will stop. Does that make sense? So, if we're talking velocity, since velocity is a vector that includes both speed and direction, and the object can speed up or slow down, then that makes sense now that there's 4 possibilities. Speeding up in a positive direction, slowing down in a positive direction, speeding up in a negative direction, or slowing down in a negative direction.
It's like when you're showing us the 4 shapes on the ground.
It's exactly that. Those 4 shapes are of the position function. So if you have an object, so let's see here. If this is the position function, we're not doing graphs right now, but just to give you an idea, okay? This means slowing down in a positive direction. This means speeding up in a negative direction. This means slowing down in a negative direction. And this means speeding up in a positive direction. Does that make sense? Now here's what I want to show you here. Since we're on the graph already, let's go with it. If this is the position function, tell me about the slope here. The slope. Positive. That means that the velocity is positive. Positive velocity. And what did we already say this is? This is slowing down positive, right? And we said that this is speeding up negative. This one is slowing down negative, and this one is speeding up positive, right? So watch this. The velocity is greater than 0, right? The velocity is positive. Tell me about the concavity. Tell me about the second derivative here. Concave down, meaning the second derivative is negative. And what is the second derivative of position? Acceleration. So here, the acceleration is negative.
Oh my gosh.
It means it's slowing down. That's correct. Now here, tell me about the velocity here. Tell me about the slope of the position. Negative, right? So velocity is less than 0. Velocity is negative. Tell me about the shape. Concave down, meaning the second derivative is
Negative.
negative, meaning acceleration is negative. Acceleration less than 0. Speeding up. You know why? Because it's moving in a negative direction, and the influence on velocity is negative. When an object is moving in a direction and the influence on the object is the same direction, what will it do? It's going to go faster in that direction. It's going to speed up. But when the object is moving in this direction, but it's experiencing influence in this direction, what's going to happen? It's going to slow down. So, when the direction of the object and the influence on the direction are the same, what will happen to the object? It'll speed up. Okay, when the direction of the object and the influence on the direction are the same. So I'm walking and you're behind me pushing me. This one right here? Right. You are having a problem with that being speeding up. Am I right? Do you know why? Because you're looking at a position function. That's why. This is not the velocity. If this was velocity, I would agree with you that the velocity would be approaching 0. This is a position function. Would you agree that up here somewhere the object changed direction? And would you agree that it stopped? Well, what's the only thing it can do after stopping? No, well, yeah, okay. But what's the only thing an object can do after stopping? It can only speed up. An object can't slow down after stopping. It is physically impossible. Right?
Negative on that graph.
I mean, you'd have to get sucked into some weird other dimension in order for an object to slow down after stopping. That's not possible.
What is negative on that graph? Like below the...
Down here,
Yeah.
where you are. This is moving in a negative direction, but you are still right of the origin. I can be on the right side of the origin and move toward the origin. Does that make sense? So, position is entirely relative, which is why on a vector graph, anybody in here ever draw vectors in some science class? Ever? Arrows, right? Lines with arrows on it? Did they tell you it doesn't matter where it is on the graph? Because the position doesn't matter. Velocity is irrespective of position. Are you in track? You understand track? Have you ever know anybody in track? Why do we have the one guy starts all the way back there, and the next guy starts up here, and the next guy starts here, and the next guy starts up there? Because of the curve, right? The position doesn't matter. What matters is how much ground they're going to cover. See what I mean? Yeah. What's that? That's what that is. Position time. Yes. Nice work, Abasi. All right, how are we feeling? Are we okay? All right, so here, slowing down, right? The only thing, other than speeding up, the only thing that an object can do after speeding up is slow down. An object can't do anything but slow down after speeding up, except for unless it's just going to continue speeding up. Right? Yeah. So here, tell me about the velocity. Tell me about the slope here. Well, but what's more important is it's going down. It's going down. Right? So the slope is negative. So the slope of position is negative. The derivative of position is velocity. Therefore, here the velocity is less than 0. Velocity is less than 0. But look at the curve. It's concave up, which means that acceleration is greater than 0. Acceleration is positive. So now,
You have a counteracting forces?
yes, it's moving in a negative direction, but receiving positive directional force. It's moving this way, but somebody's standing on the other side pushing back. And so what's it doing? slowing down in a negative direction. Here, last one. Tell me about the slope. Velocity is positive. Okay? And then tell me about the concavity. Concave up, so acceleration. Yep. So this brings us to a very, very simple rule. Those of you that are going to leave for RCA in 2 minutes, watch the video, please, because I'm going to do something very important in the next 10 minutes. Okay? Which brings us to a very simple rule. An object is always speeding up when what?
The velocity and the acceleration
Have the same sign, sign. When velocity and acceleration have the same sign, the same sign, the object will be speeding up. People have a hard time with thinking when velocity is negative and acceleration is negative that the object is speeding up. That freaks them out. They're thinking that negative acceleration automatically means slowing down. You're mixing up the idea of slowing down with a negative acceleration. All negative acceleration means is influence in a negative direction. And if an object is already moving in a negative direction, like some guy who's doing drugs, and then he goes and hangs out with a bunch of people who are doing drugs, it's going to get worse. Yep, that's it. There's nothing good that can happen with a bunch of lawbreakers getting together, especially after midnight. You know what I mean? It's not going to be good. Right. All right, so now we're going to, RCA, y'all can split, but what we're going to do now is we are going to practically and analytically identify where a graph, or when an object is speeding up and slowing down. And guess what we're going to use? We're going to use a special kind of tool. Yes, but a special kind of graph. One that I taught you how to use last semester a lot. Say again? We'll get there. Are you taking that with you?
Yes.
Yeah, okay. I wasn't sure if you were. It was like sitting there, and I was like, "Who's that?" All right. Anybody remember a special tool I taught you last year? I raved about it. Said it's so awesome. What are we dealing with here? What are we dealing? What does this mean? Remember what we said? We said if velocity and acceleration have the same sign charts. Yes, sign charts. Okay. If velocity and acceleration have the same sign, the object is speeding up. If velocity and acceleration have different opposite signs, then the object is slowing down. And people have a hard time with when the object has a negative velocity, but a positive acceleration, the object is slowing down. And people have a hard time with that too, because they're mixing up the definition of what the word acceleration means. Yes. Yes. Because if you're speeding up, it's going to look like this for a little while. But then when the friction starts having a greater effect, then it's going to look like this.
Coefficient of friction.
Yeah. So, and I don't know much about the coefficient of friction, but I'll bet as velocity gets higher, that coefficient has a stronger effect.
Yeah.
I don't know much about that. Like I don't know physics, believe it or not. I just know this stuff. I know the math of motion. Okay? All right, so here's what we're going to do. So let's say we have some position function, some arbitrary position function, which I don't have time right now to make one. What I'll try and do, you know what I should do? At home, I'll make a video, if I have time. I'll make a video of just a separate, simple example of... That was as much of a surprise for Leonardo as it was for me. A simple function where I can make this clear. But let's say that we have some arbitrary position function. Then let's say I identify the derivative of position and I get the velocity function and then I get the acceleration function. Here's what I'm going to do. I'm going to identify the zeros of the velocity function. And I am going to create a sign chart, a sign chart, okay, on the interval that is given. Let's say the interval goes from 0 to 10. And let's say, v of t, let's say that the velocity equals 0 at, I don't know, at 3 and at 8. That sounds good. Let's leave it there. Okay. And then let's say, now I'm going to identify the zeros. And let's say that the velocity is positive, then negative, then positive. Okay. And then let's say I identify the zeros of acceleration. Okay. And I'm now going to make a sign chart for acceleration on the same interval. Okay. From 0 to 10. 0 to 10. Okay. And let's say that acceleration is 0 at 2, at 6, and at 9. Okay? And that acceleration is positive, then negative, then positive, then negative. Okay? Take a lot of effort for me to try and actually figure out a situation that looked like this. So we're just going arbitrary here. Okay? You could now, with this information, you could answer the question, at time 5, is this object speeding up or slowing down? It is speeding up. Very good. Uh-huh. Because at time 5, which is about here, they are the same. Did you say? I thought you said aren't the same. Sorry. Yes, right. They're the same. Yep. Yeah. Sorry about that. So at time 5, acceleration is negative and velocity is negative. But then if you're asked, hey, identify an interval where the object is slowing down. Right, but we want to start, where does it start slowing down? You're right, the object is slowing down at 2.5. When did it start slowing down? At 2. See, look. See, we know before 2, the signs of velocity and acceleration are the same, right? But at 2, the sign of acceleration changes to negative. So then when is this period going to stop? At 3, when the sign of velocity changes. Right? And you could, a friend of mine who helped me learn how to teach calculus, he used to teach here. He taught me a technique where what you do is you make a new SIG chart. So you stack these up, and here's what you do. You bring down all of the zeros onto one line. So we're going to bring down the 2, we're going to bring down the 3, we're going to bring down the 6, we're going to bring down the house. No, sorry. We're going to bring down the 8, we're going to bring down the 9, right? And here's what you do. Now, ready? Love this. You multiply the signs. What is a positive times a positive? Positive. What is a positive times a negative? What's a negative times a negative?
Amazing.
What is a negative times a positive? What is a positive times a positive? And what is a positive times a negative? And now the signs are telling you up or down. Speeding up, slowing down. Speeding up, slowing down. Speeding up, slowing down. Isn't that neat? Isn't that great? And what we could put over here is we could say speed up, slow down, graph. Isn't that great? I'll try and put an example online of video. You guys can pack up. We're done.